Good morning, grade 8, right? We are done with the discussions with regards to the second module for the third quarter, weeks 5 to 8, entitled Atomic Structure. As promised, I will give you a lot of examples with regards to electron configuration number 1, okay? Finding out the number of protons, neutrons, and electrons with regards to its isotopes. And number 3, um, talking about the model or the how can we actually write, okay, the atomic mass and atomic weight in connection, okay, to a given element. Yes, any question? Okay, it's okay. Okay, I will be recording this one and I will be posting this one in your LMS so that you can review. Remember that your major exam, your third periodical test, is fast approaching. That will be happening this March 17, 18, and 19. So we still have 1 week to discuss and to give a lot of examples if in case you don't understand the topic, just let me know so that I can assist you. Okay? Any other concerns before we move forward? Okay. For now, I will give you an introduction with regards to the atomic trends or periodic trends rather. So you can actually see the usage of your periodic table of elements and how this periodic table of elements actually work. Okay. And the second is calculating protons, neutrons, and electrons. The basic concept of calculating protons, neutrons, and electrons. It is actually in our slide also. Okay. It is given in your modules, but this is to reinforce your knowledge, right?
Hey, it's Professor Dave. Let's talk about the periodic table.
He knows a lot about the science stuff. Professor Dave explains.
Pretty much everyone knows what this is, even if they don't know much about chemistry. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sound strange and foreign. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitry Mendeleev that stuck, because of how well it correlates data as well as its predictive powers. He arranged the elements into rows called periods and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. And it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected, and now we have all the metals, metalloids, and nonmetals organized nicely. It wasn't known at the time, but the reason elements in the same group behave similarly is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell and each element to the right has one more proton in the nucleus than the last. So there is a stronger electromagnetic attraction felt by the electrons and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron. A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look for example at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen's ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next, we will look at electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron. Disregarding the noble gases, as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains one electron, it will have a full shell, or a noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exceptions to this trend happen for exactly the same reasons as the exceptions to the ionization energy trend. Lastly, we want to look at electronegativity. This is the ability of an atom to hold electrons tightly. It will increase this way because a smaller atom like fluorine with more protons for its energy level, or a higher effective nuclear charge, will hold electrons best. Again, we will disregard the noble gases for this trend. Electronegativity will be important in the next clip where we learn about chemical bonds. So the trends to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way. Let's check comprehension.
All right, that is actually periodic trends. So there are some patterns that we need to consider in our periodic table of elements. Okay, your periodic table element is not just for us to memorize, okay, familiarize, and of course you need to consider some of the trends or some of their patterns. Okay, let's move now to calculating protons, neutrons, and electrons. It is actually given in our slide, but then again, this is again to reinforce your knowledge with regards to how can you calculate the protons, neutrons, and electrons in a given element. Okay. Hang on, let's take a look at this one.
In this lesson, we're going to talk about how to calculate the number of protons, neutrons, and electrons in an atom and in an ion. So let's use sodium as an example. And on a periodic table, you might see something that looks like this. The smaller of the two numbers is the atomic number, which is also equal to the number of protons. The larger of the two numbers is known as the average atomic mass. Now sometimes you might see a problem that's written this way. They may tell you to find the number of protons, neutrons, and electrons for this particular element. Now in this format, you can see that the atomic number is on the bottom. The number on the top, notice that it's not the same as 22.99. In fact, it's rounded. This is not the average atomic mass, but rather it is the mass number. So this is a specific isotope of sodium. If you average all of the isotopes of sodium on Earth, you're going to get this number. So because that number is close to 23, this is the most abundant isotope of sodium on the Earth. So in addition to sodium 23, you also have sodium 24, and there's also sodium 22. But as we said before, because the average atomic mass was 22.99, this is the most abundant isotope, which is also the most stable one on the Earth. The other forms of sodium, they're not stable and they're not very common, but these are other isotopes of sodium. Now what you need to know is that the atomic number is associated with the identity of the element. So sodium always has an atomic number of 11. Now the mass number can change, and it will change for different isotopes, so that number can vary. But the identity of the element is dependent on the atomic number. Now let's talk about the formulas that we need in order to calculate the number of protons, neutrons, and electrons. So let's start with the number of protons. This is always equal to the atomic number. That's it. So sodium always has 11 protons. Now the number of neutrons is the difference between the mass number and the atomic number. And then the number of electrons is equal to the atomic number minus the charge of the species. So for an atom, let's say like aluminum, which doesn't have a charge, the charge is 0. The electrons will thus be equal to the atomic number. So for an atom, the number of electrons and protons are the same because the atom is neutral. But if we have an ion, let's say a positively charged cation, then the number of electrons will change. In this case, there's going to be 3 more protons than electrons. Or if we have an anion, like the phosphide anion, there's going to be 3 more electrons than protons. So for ions, the number of electrons and protons are different, but for atoms, which are electrically neutral, the number of protons and electrons are the same. So let's start with this example. Go ahead and calculate the number of protons, electrons, and neutrons for this element. So the number of protons is equal to the atomic number, which is the smaller of the two values, so that's going to be 11. The number of neutrons is the difference between the mass number, which is 23, and the atomic number, which is 11. So it's 23 minus 11, and that gives us 12. So we have 11 protons, 12 neutrons. Now for the number of electrons, it's equal to the atomic number, which is 11, minus the charge. Now, there's no charge for this particular element. It's an atom, not an ion, so the charge is 0. So we have 11 electrons. So as we can see, for electrically neutral atoms, the number of protons and electrons are the same. Now let's consider another example. Aluminum 27 with a 3+ charge. So here we have an ion. Go ahead and calculate the number of protons, neutrons, and electrons in this ion. So we can see that the atomic number is 13 and the mass number is 27. So the number of protons is always equal to the atomic number, which is 13 in this example. Now the number of neutrons is the difference between the mass number and the atomic number. So it's 27 minus 13, which gives us 14. Now for the number of electrons, it's going to be the atomic number, which is 13, minus the charge on the ion, which is positive 3. So 13 minus 3 is 10. So for positively charged cations, there's going to be more protons than electrons. So because it has a positive 3 charge, there's 3 more protons than electrons. Now let's try a negatively charged anion. So this is the sulfide ion. And let's calculate the number of protons, neutrons, and electrons. So we have an atomic number of 16 and a mass number of 33. So the number of protons, just like before, is equal to the atomic number. So that's 16. The number of neutrons is the difference between the mass number and the atomic number. So 33 minus 16. So we have 17 for this example. And finally, the number of electrons is the atomic number, which is 16, minus the charge, which is negative 2. So 16 minus negative 2 is the same as 16 plus 2, so we get 18 electrons. Thus, for negatively charged ions or anions, you're going to have more electrons than protons. For an ion with a negative 2 charge, there's 2 more electrons than protons. Now, let's try a different example, or at least one that's presented in a different way. Find the number of protons, neutrons, and electrons in silicon 29. So in this example, we need to write this in a format that we're familiar with. So silicon 29, that tells us that the mass number is 29. But what about the atomic number? Well, we need to use the periodic table. So if you go to it, if you don't have one, you can go to Google Images. You'll find that silicon is the 14th element in the table. So it has an atomic number of 14. Now, there was no charge indicated in this problem, so we're going to assume that we're dealing with an atom and not an ion. Thus, we have 14 protons, because that's the atomic number, and the number of neutrons is going to be the mass number minus the atomic number, so that's 29 minus 14, which gives us 15. Finally, the number of electrons is going to be the atomic number minus the charge, so it's 14. So for all atoms, the number of protons and electrons are the same. Now let's work on a challenge problem. So let's see if you truly understand the lesson in this video. So we have a cation with a 4+ charge, and it has 26 neutrons and 18 electrons. What is the identity of the element? Feel free to pause the video if you want to try it. By the way, for those of you who haven't done so already, feel free to subscribe to this channel, and don't forget to click on that notification bell. But now let's begin working on this problem. So right now we're going to say that the unknown element is element X. So we know it has a 4+ charge, and the number of neutrons is 26, the number of electrons is 18. In order to determine the identity of the element, what do we need to know? Remember, the atomic number identifies the element. So if we can determine the number of protons, we can identify the unknown element. And so that's what we need to do in this example. Now, which of the three formulas that we wrote in the beginning can help us here? Is it this one? The number of protons is equal to the atomic number. Now, this is not going to help us because we know neither of these. Could we use this? The number of neutrons is equal to the mass number minus the atomic number. Now, we have the number of neutrons, but we don't know the mass number or the atomic number. So the formula that is going to be helpful is the third one. The number of electrons is equal to the atomic number minus the charge, because we know the charge and the number of electrons. With that, we can calculate the atomic number. So there's 18 electrons, and I'm just going to write A for atomic number, and the charge is positive 4. So this becomes A minus 4. So we need to add 4 to both sides, and so the atomic number is 22. And the number of protons is equal to the atomic number, which is 22. Now, if we wish to calculate the mass number, we can. The number of neutrons was the difference between the mass number and the atomic number. If you rearrange that equation, you'll find that the mass number is the neutrons plus the atomic number. Or you could say it's the neutrons plus the protons, because the protons is the same as the atomic number. So it's 26 plus 22, which is 48. Now, granted, that last step wasn't really necessary, but I decided to do it anyway for those of you who were curious on how to get it. But let's focus on this number. So if you go to the periodic table and look for element 22, let me get mine real quick. You'll find that this corresponds to titanium. So this is the titanium 4+ ion. And this is the answer. So titanium is the unknown element. And that's how you can identify any unknown element for these types of problems. Once you identify the number of protons, you could use the periodic table to identify the missing element.
All right. Do you have any questions so far? Again, how can we get our protons, the number of protons? It is actually equal to the atomic number, of course. Okay. The second one, how can we get the neutrons? This is the atomic mass, okay, minus the atomic number. Okay. And how can we get the set of electrons? This is atomic number minus the charge. It could be positive or negative. Okay. It could be a cation or an anion. Okay. What else? Talking about isotopes. Okay. In the given illustration, in your exam, okay, I'll be giving you a lot of isotopes. Okay. It could be more than its atomic mass, or it could be lesser than its atomic mass. Okay. If you are tasked to give the atomic mass of particular element, without actually, if I will not put it, I will not put the atomic mass or an isotope. By the way, what is an isotope? Okay, talking about isotopes, these are the different versions of particular element. It could have more than its atomic weight or atomic mass, or it could have a lesser atomic mass. Okay, it depends upon. Isotopes are said to be unstable. because they're unstable, it needs to be stabilized with another element or with an action of a particular element, right? So if you are actually tasked to identify the protons, neutrons, and electrons, but I didn't actually put atomic mass on it, simply use what is in the periodic table of elements, use the stable one. Like for example, if the atomic weight or mass is equal to 29.9, round it off. Use 30. Okay? If the atomic mass is 28.7, round it off. But if the atomic mass is 28.3, use 28. Okay? Just round it off to its nearest number if the given didn't actually include the atomic mass. Use the periodic table of elements. That is why I'm requiring you to download your own periodic table of elements. For the examples of for the examples of these protons, neutrons, and electrons, I will be giving this one by the next meeting. Okay, even the electron configuration. Okay, examples for the electron configurations will be given by next meeting. Okay, let's stick with the introductory videos that I actually given to you, and of course, the activity for today. What I want you to do now is I want you to go to your LMS and answer activity number 1, which is modified enumeration. Again, do not wait for tomorrow what you can do for today. This activity will close by this afternoon. That's around 5 p.m. And I'm expecting answers from you, right? These are the concepts that we actually discuss. Okay? All you have to do is to enumerate those and discuss it by your own words. Okay, how many items is this? If you're going to look at this is 45 items, right? And again, we have limited time with regards to answering your activities. That is why this is actually what? Concentrated activities. So we have limited activities also, right? Without the absence of one activity can actually give your grade a big remark, right? A big changes. All right? Do you have any questions so far? Questions? Still have 9 minutes. Do you have any questions so far? Grade 8? Are you still with me? Grade 8?
Yeah.
All right. Again, please answer activity number 1. And by next meeting, hopefully you can move to activity number 2. I think that will be for today, class. Thank you for your participation. Again, I have only 3 students here. The rest are absent. Have a nice day, grade 8. Take care. Bye-bye.